Hello, I'm Emre Karaca. We are Group 35. This is our video presentation. Our topic is autonomous navigation and deep learning-based obstacle detection in unmanned ground vehicles. Let's get started. Our team distributed work by discipline and measurable deliverables. I led system integration and validation under work package 5. Yunus owned the deep learning pipeline. Furkan handled power and chassis integration. Ahmet developed the embedded firmware, and Ali led planning and state machine logic. Each task carried a concrete acceptance metric like MAP scores or battery autonomy. The engineering problem is a persistent trade-off in mobile robotics. Cameras fail under poor lighting, 2D LiDAR is blind to volumetric hazards, and 3D LiDAR systems are too expensive and power hungry for edge platforms. The need we identified is a perception system that delivers safe operation on resource-constrained hardware. Our answer is a hybrid architecture, which we can say 3D safety on a 2D budget, which runs entirely on the NVIDIA Jetson platform, with appropriate safety measures included. Between the detailed design and the implementation phase, we deliberately reframed engineering requirements 1 and 3 towards a structured parkour testbed. This made central hypothesis measurable within budget and time.
Hello everyone, I am Furkan Sarıyerlioğlu. I'll explain the hardware integration and system architecture of our vehicle. On this slide you can see our level 0 and level 1 diagrams. We isolated safety critical functions from the high-level deep learning logic. This independence ensures that even if the AI layer crashes, the vehicle remains safe. Moving to the level 2 diagram, you can see how this separation is physically realized. The main computer Jetson or in Nano handles the heavy lifting of perception and planning, and it sends motion orders to completely separate microcontroller. This modularity guarantees deterministic motor control and clear data transfer. For the physical platform, we used an RC chassis with a custom structure. Major implementation choice was using separate power domains. By doing that, we protect the Jetson from electrical transients. We also optimized our physical design by replacing Arduino Mega with much more compact Arduino Nano. These schematics detail LED power isolation. On the top you can see logic domain, and the bottom side is the motor domain. During implementation, instead of complex current sensor and e-stop, we integrated a basic fuse. It perfectly meets our power safety requirements while reducing complexity. Also, the Arduino Nano acts as a failsafe, automatically cutting motor power if the serial connection to the Jetson drops. Thanks for your attention.
Hello, my name is Yunus Gündüz. First, how does our vehicle see? We trained a custom dataset for sign and lanes. We choose the YOLO V8 small model for the best speed and accuracy balance. Processing takes under 200 milliseconds, allowing the car to react instantly. For lane tracking, we use a bird's eye camera view. We combine this with LiDAR and motion sensors, just like humans use eyes and balance together. Finally, a control algorithm prevents drifting during sharp turns. The car plans a route like a GPS. It compares real-time signs with the map and stops if they don't match. If the AI fails, independent safety systems like emergency braking take over immediately to prevent accidents. And we tested 3 AI models. All reached about 97% accuracy. Since accuracy was equal, speed was the tiebreaker. We choose YOLO V8 Small because it was the fastest on our hardware. Finally, the testing phase before physical deployment, we tested the software in a virtual simulator, like a pilot in-flight simulator. This risk-free environment let us safely tune algorithms without crashing the real vehicle.
My name is Ali Gaisea. Today I'll be starting with the test strategy overview, validate the system in 4 tires, unit, model, integration, and acceptance. We've done 30 tests and they all passed. Moving on to the unit slides. Unit test checks each component in isolation and all were verified physically on the bench. You can see in the table the most important unit test and their expected criteria. Moving on to the module. At the module level, we test each function, subsystem on its own. The RPD driver gives a stable scan topic on the bench. Our YOLO VE8 sign recognition hits a mean average precision of 0.95 or higher. You can check the other tests from the table. Moving on to the integration. Integration tests can check that models work together correctly. Like computer vision feeding the PID steering keeps us within about 4 centimeters of the center line. We also test a curve warning sign correctly. It reduces the speed 35% before the bend. Moving on to the acceptance. Acceptance tests verify that the complete system satisfies the top level engineering and marketing requirements. Hardware dependent tests, for example, e-stop, battery, autonomy, bomb cost, were verified on bench. Functional acceptance tests were validated in Gazi simulation. Moving on to the traceability. This table traces every engineering requirement to the specific test that verify it. Object detection passes physically at 0.97 MAP, the under 200 millisecond latency, the hardware independent, emergency stop, the limit, the speed limit, the 4 hours battery life, all pass physically, while sign, obstacle, and crosswalk handling pass in both simulation and on hardware, which is physically. Several accepting cases are validated in simulation rather than on the full physical parkour. The remaining gap is the full physical acceptance trial, which is our work package number 5, and it's still ongoing. Moving on to the cost analysis, this is our realized bill of materials. The dominant costs are the Judson Oil Nano, which costs us 18,000 TL, and the depth camera is about 24,000. The grand total is 55,459. As you can see in the table, every line item is justified by its function. For example, the camera provides both detection frames and depth verifications.
Hello, my name is Ahmet Furkan. I will be presenting the cost optimization, commercialization plan, standard and multidisciplinary aspect sections. First, cost optimization. We reduced the material cost to under 60,000 Turkish liras. These did not result in a decrease in functionality. This contribution margin is approximately 30,000 Turkish liras per unit. This means our entire fixed investment is recovered after selling just 2 units. Safety runs at 3 independent layers: hardware fuse cutoff, software speed limits, and dual sensor perception redundancy. ROS2 convention followed, LiPo handling meet UN, and camera data processed on edge with no storage. These projects span 3 disciplines: electrical electronics for power and embedded control, computer engineer for the AI perception and route stack, and mechanical engineering for custom sensor, mount and drivetrain isolation. With special thanks to Ahmet Taşkapı for his contribution. SDG 9 through low-cost autonomous navigation, and SDG 11 through sign and crosswalk handling for safe cities. Thank you for listening.